that in nuclear physics, in nuclear physics, we have two topics to learn. Number one, it's the nuclear model of atom, nuclear model of atom. And number two, it's the radioactivity. Radioactivity. All right. When I talk about nuclear model of atom, you have two subtopics in this section. Number one, it's the atom, and number two, it's the nucleus, right? And if I talk about radioactivity, you have five things, or in fact, six topics in radioactivity. So, listing them down one by one, the first thing is radioactivity. Sorry, it's detection of radioactivity. Number two, it's the three type of emissions. Three type of emissions. Number three, it's the radioactive decay. Radioactive decay. Number four, it's fission and fusion. Fission and fusion. Number five, it's half-life. And last, number six, it's safety precautions. Safety
Oh, sir, remember this.
precautions. You've done this?
No, sir, I did this last year, sir. Half-Life is so annoying.
All right. You'll find it better this time, inshallah. Okay. So, talking about the nuclear model of atom. Now, if I talk about the nuclear model of atom, uh, we should know the basic structure of atom in terms of a positive nucleus and negative electrons orbiting the nucleus, right? So if you find this central part of the atom, this is nucleus, which consists of protons and neutrons, right? And then you have these electrons revolving around. You would find that the nucleus is positively charged. Nucleus is positively charged. The electrons are negatively charged. Why is nucleus positive? Because it has protons and neutrons. Neutrons have zero charge while protons have a positive charge. So that makes this whole nucleus a positively charged particle, right? Okay, now one more thing that should come into your mind is that if I talk about the nucleus, it's positively charged. Okay, fine. What makes these positive charges to be bound strong inside the nucleus despite they being repulsive? Because protons repel, right? If they're repelling and they're still bound inside the nucleus. Who is making them bound? So it's the strong nuclear force. It's the strong nuclear force that makes it bound inside the nucleus. Now, see, if I talk about the fundamental forces of nature, there are four. One is the gravitational force. One is the gravitational force. This gravitational force is present between what? This gravitational force is present between two masses. We have the next fundamental force of nature, which is electrostatic force. This exists between two charged bodies. You have magnetic force. This exists between magnetic fields. And lastly, you have this nuclear force, which is very, very, very strong, but it's very, very, very short range. Means the nuclear force only acts inside the nucleus. Outside the nucleus, it has no what do you say, it has no power, or it cannot keep things bound together. So it makes the nucleus, and it makes the protons to exist inside the nucleus. This is due to the nuclear force, strong nuclear force. If I somehow am successful in removing one of this neutron just a little outside the nucleus, then it cannot be held there. Why? Because it's outside the range of the nuclear force, right?
Yes, sir.
So you have protons and neutrons present inside the nucleus that makes the nucleus positively charged. Now, most of the nucleus is empty space, and all of the mass of the nucleus is concentrated. Oh, sorry, all of the mass of the atom is concentrated at the center. At the center, that's inside the nucleus. And if I talk about the relative masses of these subatomic particles, you will find that proton has a relative mass of 1 and it has a relative charge of plus 1. Neutron has a relative mass of 1, it's neutral, it has no charge. Electron is very small, so you can almost say it has no mass, and it has a relative charge of minus 1. So this is how the charge and masses of these subatomic particles behave. Now there are some things that we need to take care of. What are they? Number one, we need to have an evidence. We need to have an evidence that that the atom is empty space. Atom is atom is empty space, empty space, and small nucleus. The nucleus is small. We need to have an evidence for this. We need to have an evidence for this also, that the nucleus is positively charged. Nucleus is positively charged. We need to have an evidence of this also, that most of the mass of the atom is in nucleus, is concentrated in nucleus, right? We need to have a proof for all these. Now, in order to go and find a proof for all these, we'll have to understand Rutherford's alpha particle scattering experiment. Alpha particle scattering experiment. Alpha particle scattering experiment. We need to understand that. All right. Now, what is alpha particle scattering experiment? This was done by Rutherford, and let's see how does it look like. What's the experiment? Alpha particle scattering. Alpha particle scattering experiment. All right. You can see that Mr. Rutherford, he made use of what? He made use of not this. Uh, All right. So what he did, he made a screen just like this, the black one I'm highlighting. I hope you can see my screen.
Yes, sir.
He made the screen. He placed an alpha particle source, a source that was giving out alpha particles, that was emitting alpha particles, right? And when he did that, he placed an aluminum foil in front of it. He placed an aluminum foil in front of it. Okay. When these alpha particles that are emitted by this source, they went out and they strike the screen used to scintillate. The screen sparks were seen on the screen. What? Sparks were seen on the screen, right? So when he let these alpha particles to hit the screen, he found that there were some sparks created there, some scintillations created there. He found that most of the sparks were seen right in front over here. Most of the sparks were seen right in front over here. That means that most of the particles went through straight through the foil, undeviated, undeflected, right?
Yes.
But all right. He also found some particles to bend slightly, change their path, get deviated from their path slightly like this. I hope you see the markings I'm making. So these particles got deflected. These particles got their paths changed by a small angle. By a small angle. Why? Because this was the original path. And these particles got deflected a little bit like this, like this, like this. So they were deflected by a small angle. And the third thing he saw was that even the smallest number of particles, they deflected at large angles. So this was the original path, see, and this is the angle that this particle got deflected in. This is the angle that this particle got deflected in, right? So these two particles, these very few particles, got deflected or got reflected back, with large angles, right?
Yes.
So there were three observations. Number one, particles that went through straight. Number one, particles that went through straight. Number two, there were particles that got deflected with small angle. So small angle deflection. Small angle deflection. There were particles that deflected at large angles, right? Large angle deflection, right?
Yes, sir.
He made these three observations. Now these three observations, what he saw, what he concluded from the first observation was that atom is empty space, right? And the nucleus is small. Nucleus is small. From this observation he concluded that the nucleus is positive. The nucleus is positive. And from this observation, he concluded that all the mass is at the center. Because if the mass was not at the center, he would have seen deflection somewhere else as well. But he just saw very few deflections that were bouncing back right from there at very large angles, right? So he concluded that the mass is concentrated in the nucleus. Mass in nucleus. So there were three observations. How many? Three. Number one, most particles went through undeviated, undeflected, unchanged. A very small number got deflected by a small angle, and even the smallest number got deflected by large angles. So with these three observations, he concluded that the atom is empty space. Most of the nucleus is small, And then the second observation, which was deflection at large angles, he concluded that the nucleus is positive. And in the third case, he concluded that all the mass is concentrated inside the nucleus. Is that clear enough?
Yes, sir.
To emphasize this further, demonstrate this more better, so I'll take you to this animation on alpha particle scattering experiment. Here it is. Can you see my screen?
Yes, sir.
So see, this is one atom, this is the second atom, this is the third atom. You have a nucleus at the center, nucleus at the center, nucleus at the center. So you have three atoms. This is the alpha particle source. This is the alpha particle source. So this is, let's say, this whole sheet is a gold foil, and these are gold atoms, and you have placed your alpha particle source, this one right here. When I switch this on, alpha particles will start to come out from here, and go through this just like this, right? So
Yes.
let's see what happens. As I switch on, I'll just switch on the traces too. Okay, wow. So you can observe what you see, most of the particles going straight through. Just look at it, how satisfying it is. Observe it for a while.
Particles in the nucleus are getting repelled.
Sorry?
The particles near the nucleus are getting repelled.
Yes. And these alpha particles have a positive charge. Alpha particles have a positive charge.
Pro-
So who can repel an alpha particle then?
Protons.
Right? A positive charge. At that time, they did not know about protons. At that time, they did not know about protons, right?
Yes, sir. That most of these experiments of these found on accident.
Just say it again, please.
So isn't it interesting that most of these like experiments were found on accident?
Uh, I was not able to hear you properly.
So it's interesting that most of these experiments were done on accident.
On accident? Why?
No, sir, because a lot of the experiments, like in physics, are they discovered it by accident somehow.
Yeah, they were experimenting and they found out something new, right? So at that time, they did not know about protons and neutrons. They just discovered that there's this, and at that time, there was a time when scientists considered atom to be the smallest particle. Then they discovered it further. No, atom is not the smallest particle. You have a nucleus inside it, and you have electrons around it. They did not know about protons and neutrons then, right? So later on, they found, okay, not the atom is not the smallest particle. Other than neutrons, other than electrons, you have neutrons and protons inside the nucleus as well. Then they found, okay, neutrons are the smallest particles, and protons and electrons. They went on to find that not even the neutrons and protons were the smallest particles. Rather, you have more subatomic particles too. That is, neutrons and protons. They have some flavors which you call as charm, strange, up, down, and so on. Right. So you have a lot of science ahead of this too, but to our syllabus we'll only be dealing the smallest particle as the proton, neutron, and electron, right?
Yes, sir.
So, okay, you see that, just let me take a screenshot. All right. So if you look at the screen, you will find that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 14 particles that are going straight through, right? Even this particle, 15, 16, 17, right? So they are going straight through. You can see a very small number like this one, bending, deflecting. Now it's positive. So who can repel a positive? A positive particle can repel. So that means this nucleus is positively charged. Hmm? So one particle that deflected is this one. The other particle that got deflected is this one. So you just see out of these around 20 particles, you just see this one, this one, and this one getting deflected, right? And you find rest of them going straight through. You find this one deflecting at a very large angle. Hmm? So this indicates what? That mass is in nucleus. Mass in nucleus. Mass is in nucleus. This particle indicates what? It indicates that nucleus is positive. This indicates that nucleus is positive. And rest of the 16, 17 particles, what do they indicate? They indicate that the atom is mostly empty space. The atom is mostly empty space. If I make an analogy, let's consider there's a largest stadium in the world, and you evacuate all that stadium, and you just place a peanut at the center of stadium. So that peanut is the nucleus, and the whole stadium is the atom, right?
Yes, sir.
So this is how an atom can be analyzed. I hope you understand that. There is no problem, no confusion.
Yes, sir.
So I would want you to note all these down now in your notebook.